Today we're going to look at multivariable linear systems. So a multivariable linear system is a system of linear equations that have two or more variables. And we know we've seen this before, where we've solved systems of three equations and three unknowns. We're going to do the same thing, but using various different approaches, one of them being matrices. So you already know that by substitution or elimination, we can solve a system. What we're going to do today is we're going to use use these methods to put the system in triangular form or row echelon form. So what is row echelon? Basically, it's in triangular form like this. So what you do is you're going to eliminate some of the variables to get the system to look like this, where the first row has x, y, and z, the second one has y and z, and the third one has just z. This process is called Gaussian elimination. All right, so there are some operations that you can do that are basically free. They don't cost you anything. Some of those are, you can interchange any two equations, so you can swap them, exchange their places. You can multiply one of the equations by a non-zero number, or you can add a multiple of one equation to the other. This is what we would call elimination previously. All right, so here's a series of steps on how to solve one of these. So first we want to eliminate the x term in equation 3. And the way we do this is by replacing equation 3 with the sum of multiples of equation 3 and another equation. After we eliminate the x term in equation 3, we want to eliminate the x term in equation 2. Next, we eliminate the y term in equation 3. And at the end, we want to make sure that the leading coefficients of each of the equations are 1. All right. So let's go ahead and do our very first one. Okay, first off, a little bit of notation. So I call these E1, E2, and E3 for equation 1, equation 2, equation 3. Now, you want to do this in a variety of ways. It's easiest to stick to the way I've told you. So first eliminate the x in the last one, then the x in the second one, and then the y in the last one. All right. So what makes this easier? Well, first of all, what I want to do is I want to divide everything in equation 1 by 5 so I can work with smaller numbers. Now, the reason behind calling these E1, E2, E3 is that each step you want to keep track of what you're doing so you can go back later if need be. So the first thing I'm going to do is 1 over 5 E1. Later on, we're going to call these rows, but now I'll get away with equation 1. So when I do that, I get x minus y minus z is equal to 7. Negative x plus 2y minus 3z is negative 12. 3x minus 2y plus 7z is 30. Now, we said this is the first term I want to get rid of. Okay. That means the other two equations, 1 and 2, are going to remain unchanged. Now, how do we get rid of this 3? Okay, so basically it's just like the elimination process we used before when it was just two equations and two variables. I want to see, okay, what can I combine this with in order to make the x go away? Well, what if I multiply the second equation by 3 and I add it to this? So that would be 3 E2 plus E3. So negative 3x, positive 3x goes away. 6y minus 2y is 4y. Negative 3 times 3 is negative 9, plus 7 is negative 2z. equals negative 36 plus 30 is negative 6. All right, next, let's get rid of negative x. So let's eliminate negative x. All right, how am I going to do that? Well, the first equation will remain unchanged. And the last equation will remain unchanged. Now here, to get rid of this negative x, I can just add equation 1 plus equation 2. Let's just do that. Equation 1 plus equation 2. So the x's go away, and I have y minus 4z is equal to negative 5. Okay, great. All right, so now what am I going to do? Now I need to eliminate the 4y. All right, that means first equation stays unchanged. Second remains unchanged. Now, for the third one, how do I eliminate 4y? Well, what I want to do is I want to multiply equation 2 by 4. So 4 equation 2 minus equation 3. All right, so let's do that. 4y minus 4y will be 0. Negative 16 minus negative 2, so let me write that here. Negative 16z minus negative 2z will be negative 14z. And here I have negative 20 minus negative 6. That will be negative 14. All right, so finally, we can get rid of the negative here and the negative there and divide by 14. So what do we have? X minus y minus z is equal to 7. Remember, the last step is to make sure that all the leading coefficients are 1. In the first row, the leading coefficient is 1. In the second row, the leading coefficient is 1. Here, I just need to divide by negative 14. So I'm going to get y minus 4z is equal to negative 5. And z is equal to 1, right? So there we have it. This is row echelon form. And now I could just go back and I could solve it with absolutely no problem. All right. To solve, we use what we call back substitution. So I know that z is equal to 1. And now I just keep substituting from here to the previous row and from there to the previous row. So the row previous to that is y minus 4z is equal to negative 5. Y minus 4 times 1 is equal to negative 5. Y is equal to negative 5 plus 4, which is negative 1. And then x minus y minus z is equal to 7. X plus 1 minus 1 is equal to 7. So x is equal to 7. Remember that these are 3 lines that intersect in space. So we have to give our answer in the form of a coordinate point. 7 minus 1, 1. Okay? And it's always in alphabetical order. X, Y, Z. So there we go. This is how we would solve it using row echelon form and Gaussian elimination. All right, so when solving multivariable systems, you notice that the variables remain untouched. We're basically just carrying along the variable, and they're not, the x, the y, the z are not making any contributions to it. They're just labels that are being tacked along. Well, what if we could eliminate the x, the y, and the z? What if we could just deal with the coefficients, right? That would make things so much more efficient. Well, that leads us to the ability to solve these using a matrix, which lists the coefficient and the constant terms only. This is called an augmented matrix. So look, if here we have the system of equations, if I only take the coefficients 5 minus 5 minus 5, 35, right? So this is the matrix of the coefficients of the equations, and these are all the constants right here, right? I separate the coefficients from the constants using a dotted line, and this is called an augmented matrix. Sometimes it's necessary to just look at the coefficient matrix on its own, and that's what that coefficient matrix looks like. Now, we can do to this augmented matrix the same exact operations as we did here, except we only have the numbers, none of the variables. We are allowed to interchange any two rows. We're allowed to multiply one row by a non-zero number. We're allowed to add a multiple of one row to another row. It's really quite fascinating. Before we get there, all right, how does an augmented matrix in row echelon form look? Well, the way it looks is here. When you've got the main diagonal of ones, everything underneath the main diagonal are zeros, right? And everything above has the other coefficients, right? So in addition, rows consisting entirely of zeros have to be placed at the bottom like this, right? So let's see if any of these are in row echelon form. We'll take a look at this one. This is the main diagonal. Is everything underneath it zero? Yes. So yes, this is in row echelon form. All right, take a look at this one. You see that this one fails. You've got a row of zeros here, which is not in the bottom, and your main diagonal is not all ones. So this is definitely not. It's got all sorts of problems happening there. Well, look at this one. The row of zeros is neatly placed at the bottom, and on top, you've got the main diagonal, underneath which all the numbers are zero. So this is definitely yes in row echelon form. All right, so to solve it, we're going to be consistent with what we did before. These are tips and tricks. It really makes it easier, I've noticed. So we're going to start with the entry in the bottom left corner. Okay, so the A31 entry, right? So the bottom left corner, this one here. Whoops. So we're going to start with this one here. Second, we're going to eliminate A21, the one right above it. Next, we're going to eliminate A32, right? So if I have a matrix that looks like this, the order in which I eliminate them is, this is the first one I make go away, then this one, then this one. This is by far the simplest, easiest way to do it. And I promise you, if you stick with this, your life is going to be so much easier. All right, this should look familiar. It's the exact same matrix from before. You know what? We're going to solve it using a matrix now. All right, so let's do that. So first I write it down as an augmented matrix. 5, -5, -5, 35. -1, 2, -3, -12. 3, -2, 7, and 30. All right. We have to have the brackets and this line. You don't have to make it dotted. It's totally fine if you make it a solid line. All right. So what we're going to do first. Now remember, everything in the first column are the coefficients of the x's. So we say this is the x column. These three numbers are the coefficients of the y's, and this is the coefficient of the z's. All right, so what I'm going to do first is 1/5 times row 1. Now I call these row 1, row 2, row 3. So it's going to be 1/2 row 1, because I want to divide everything by 5 and make these 1, -1, -1, 7. All right, it's so much easier to do it that way. Now, let me copy this down. Now, actually, we don't have to waste an entire step on just eliminating one. We could eliminate more than one at the same time, right? So, okay, how are we going to do this? Well, first of all, the first row is going to remain unchanged. Now, I said what I wanted to do is I wanted to eliminate this one first, right? So how am I going to do that? Well, what if I multiply row 2 by 3 and add it to this one? So 3 row 2 plus row 3. That'll be negative 3 plus 3, 0. I have to put in all the numbers, including zeros. All right, 3 row 2 plus row 3. So that's 6 minus 2 is 4. 3 row 2 plus row 3. 9 plus 7 is 16. Now, I'm sorry, this is negative 9 plus 7, so it's negative 2. 3 row 2, negative 36 plus row 3 is negative 6. Now, in the same step, I could also get rid of this one, right? All I have to do is add row 1 plus row 2. I can totally do that because they're independent of each other. Why waste ink? So this is going to be 0, 1, negative 4, and negative 5. All right? Now, what's left to eliminate? So what did we do here? We did row 2 plus row 1. All right, what's left to eliminate here? Well, this is the next one I want to eliminate. Well, how am I going to do that? I'm going to do 4 row 2 minus row 3. Or how about this time we do negative 4 row 2 plus row 3. Can we do that? Why not? So negative 4 plus 4 is 0. Well, let's start with the first term. 0 plus 0 is 0. Negative 4 plus 4 is 0. Positive 16 minus 2 is 14. Positive 20 minus 6 is negative 14. Positive 14. And get rid of this stuff. My scratch work over there. Right? Now, the other rows were left unchanged, right? All right, now I want to make this first one a 1. So I need to divide both by 14. Right, 1, negative 1, 7, 0, 1, negative 4, negative 5, 0, 0, 1, 1. Okay, there we go. I'm done. Look at my leading diagonal. Look at my main diagonal. That's a 1. Everything underneath is zeros. We're done. Now, remember I had said this is the X column and the Y column and the Z column? So if you look at the bottom row, it's 0x plus 0y plus 1z equal to 1, right? So from there, I can gather that z is equal to 1. And from the row right above it, 0x plus 1y minus 4z is equal to negative 5. Well, y minus 4 times 1 is equal to negative 5. So what is that equal to? Y is equal to negative 1. This x minus y minus z is equal to 7. X plus 1 minus 1 is equal to 7. So x is equal to 7. And finally, my answer is 7 and minus 1 and 1. All right, so there we go. Gaussian elimination. Now, so Gauss comes up with this. Then this other scientist, Jordan, comes along. That's his last name. And he says, you know, why stop here when you could just go further and also eliminate the numbers above the main diagonal? And you can make it look like this, where the main diagonal is 0, where the main diagonal is 1, everything below is 0, everything above is 0. So you just have the main diagonal of 1s and everything else is 0s. And you know what? That eliminates doing this back substitution, right? We call that reduced row echelon form, and it's given the name Gauss-Jordan elimination. So remember, Gaussian is going halfway. Gauss-Jordan has an added name. You just go all the way, right? If we can, so basically all you do is you continue the process of applying row operations and just reduce the other ones as well. So let's do one. Here we go. We're going to write this as a matrix, first of all. So it's going to be 1, minus 1, 1, 3, negative 1, 2, negative 1, 2, 2, negative 3, 3, 8. Now, the first thing we want to get rid of is this one. And the way I'm going to do that is I'm going to multiply row 2 by 2 and add it to this. So I'm going to do 2 row 2 plus row 3. All right, and I'll just go one step at a time here. So the first 2 rows remain unchanged. Now, the bottom row definitely changes. So negative 2 plus 2 is 0. 4 minus 3 is 1. Negative 2 plus 3 is 1. 4 plus 8 is 12. Okay, all right. Well, which one do we get rid of next? Well, next, I want to get rid of this one. Well, how am I going to get rid of that one? How about if I add row 1 plus row 2? That'll totally work. Now, row 1 stays unchanged. Row 3 stays unchanged for now. All right, I'm going to add row 1 plus row 2, and I'm going to get 1 minus 1 is 0. Negative 1 plus 2 is 1. 1 minus 1 is still 0. 3 plus 2 is 5. All right, now, which one am I going to get rid of next? Well, this one. I'm still going in the same order, right? So when you do it in this order, in the first, spaces in the first entries for the second and the third rows, you get zeros. So when you add those 2 bottom rows together, you're just adding zeros for the first number, and it's just so much simpler. All right, so how am I going to get rid of that green 1? Well, how about if I do row 2 minus row 3? That should work. All right. Now, first row, untouched. Second row, untouched. Third row will change. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 is negative 1. 5 minus 12 is negative 7. So now, I know somebody is asking, well, wait, couldn't you have done row 3 minus row 2? Totally. Would that have saved you a step? Totally. Okay, that's totally fine. Now, do I need to show work to cancel these ones? You know what, in Precalc Honors, no. Let's just make these positive, positive. All right, so what do we have now? What else do I have left? Well, what I want to do now is I want to change all these other numbers, right? So now I do it backwards. The one I want to get rid of first is this, right? So how am I going to get rid of that 1? Well, what if I do row 2 plus row 1, or row 1 plus row 2, since they're commutative? All right, 1 plus 0 is 1. Negative 1 plus 1 is 0. 1 plus 0 is 1. 3 plus 5 is 8. All right, these 2 will remain unchanged. Okay, which one do I have left? Well, this last one. Okay, how am I going to get rid of that one? Well, what if I do row 3 minus row 1? Okay, or row 1 minus row 3. Let's do that. Row 1 minus row 3. I'm going to get 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. 8 minus 7 is 1. Look at that. 0, 1, 0. 0, 0, 1. I got a 5. I got a 7. Is that reduced row echelon form? Yes, it is. All right. Now, what does this tell us? This is the X column and the Y column and the Z column. You know what this tells us? This tells us we're done. Because 1x plus 0y plus 0z is equal to 1. So basically this says x is equal to 1. 0x, 1y, 0z is equal to 5. What does this tell me? Y is equal to 5. Nothing here, nothing here. Z is equal to 7. So what's the answer? 1, 5, 7. Always in coordinate form, never in that form. All right, let's move on to some special cases. So when it's impossible for the matrix to be written in reduced echelon form, there are two possibilities. Either no solution or infinitely many solutions. Okay? All right. So let's do this first one. 1, 2, 1, 8, 2, 3, minus 1, 13, 1, 1, minus 2, 5. All right? Now, what I want to do is get rid of this one first. And the way I want to do that actually is row 1 minus row 3. So when I do row 1 minus row 3, 1 minus 1 is 0. 2 minus 1 is 1. 1 minus negative 2. 8 minus 5 is another 3. Now, this is the beauty of this, all right? In one step, I can tackle two processes, right? So I want to also get rid of this 2. How am I going to do that? Well, what if I multiply row 1 by 2 and subtract from that row 2? So 2 times 1 minus 2 is 0. 2 times 2, 4, minus 3 is 1. 2 times 1 minus 1 is 1. I'm sorry, it's not 1. 2 times 1 minus negative 1 is 3. 2 times 8 is 16 minus 13 is 3. Oh my, look at that. So now I have 1, 2, 1, 8. Okay, so what if now I want to get rid of this one? Well, I want to do row 2 minus row 3, right? Well, what does that give me? 1, 2, 1, 8, 0, 1, 3, 3. And on the bottom, I get 0 minus 0, 0, 1 minus 1, 3 minus 3, 3 minus 3. I get a whole row of zeros. Well, what does that mean? 0 equal to 0. When is 0 equal to 0? All the time. That means this is infinitely many solutions. Now, do I leave it like that? No. What I actually want to do is I want to get it in a form where I can plug in and generate values, right? Okay, so what we do is this. We write down what we have from the first row. So it's x plus 2y plus z is equal to 8. And the second row tells me that 1y plus 3z is equal to 3. Well, what I want to do now is I want to solve this one for y, okay? So when I do that, I get y equals 3 minus 3z. I'm subtracting 3z. All right, now what I want to do here is solve for x and then substitute y. All right, so basically, look, it was the third row that went away, right? Oops, sorry. It was the third row that went away. And right, so we have information on the x and the y. We have no independent information on the z. So we want to get rid of all the z's. All right, so let's see what we're going to do here. So what is x here? X is equal to negative 2y minus z minus 8. Okay, now I want to substitute y. So let's go ahead and do that. X is equal to negative 2, 3 minus 3z minus z minus 8. This is equal to negative 6 plus 6z minus z plus 8. So x is equal to 5z plus 2. All right, so what do we do now? I have my x, my y, and my z again, right? What did I just get for x? 5z plus 2 from here. What did I get for y? 3 minus 3z. And for z, I just enter z. And that's my general form for this, right? So basically, you have to pick one variable. Normally, it's z, and you have to solve everything in terms of z. Now, what this is used for is I could generate any numbers that are going to be the solution set for this. So I say, okay, what if z was equal to 1? Well, then x would be blah, 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 y would be blah, 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 and I could generate a point. Okay? All right, so let's do this next one. Here, I'm going to get 2, 3, minus 1, 1, 1, 1, minus 2, and 5. 1, 2, 1, 8. Yes? Okay. Let's get rid of this one. I want to do row 2 minus row 3. 0. 1 minus 2 is negative 1. And negative 2 minus 1 is negative 3. And here I get 5 minus 8 is negative 3. Now, at the same time, I want to get rid of this. So I want to do row 1 minus 2 row 2. 2 minus 2 is 0. 3 minus 2 is 1. Negative 1 minus 2 times negative 2 is negative 1 plus 4, which is equal to 3. 2 minus 5 is equal to negative 7, negative 3. I'm sorry, that was supposed to be 1 minus 2 times 5, 1 minus 10, which is negative 9. And here I have 2, 3, minus 1, 1. All right. Okay, which one do we want to get rid of next? Well, this one. So how are we going to do this? Well, I want to add row 2 plus row 3. So my first 2 will remain unchanged. Now, adding row 2 plus row 3, 0 plus 0, 0, 1 minus 1, 0, 3 minus 3, 0, negative 9 plus negative 3 is negative 12, and here we have a problem because this is telling me that 0 is equal to negative 12, and my, that never happens. So the answer to this is no solution. All right? So this is the problem set that you will be working on next. Thank you.